The ocean is different from lakes and rivers for two primary reasons. First, the ocean is the largest water body on Earth, and second, ocean water is salty. The salinity or saltiness of the ocean is a measure of how much salt has been dissolved or mixed into the ocean. Thus, two of the most important characteristics of Earth's oceans are the temperature of the ocean and its salinity. Together, temperature and salinity determine the density of water, which is a major factor in controlling the circulation and vertical movement of ocean water. Density-driven circulation accounts for 90% of all of the movement of water, such as ocean currents, that we see in the ocean. Water movement of this type, the part that is controlled by density circulations, is also called the thermohaline circulation. Thermo here corresponds to the concept of temperature, and haline is another form of thinking about salinity or salt content. Colder and saltier water is heavier than warmer and fresher water. So what we're going to show in this video is why is it that the differences in temperature and the differences in salt content of water leads to a circulation pattern similar to the figure that you see on the video. Using a density circulation apparatus or platform, we're going to go through a series of experiments to investigate the effects of temperature and salinity on both water density and the corresponding circulation. To examine density-driven circulations, we're going to use the apparatus that you see in front of you right here. This is simply just called a density circulation tank or a density circulation apparatus. If we bring this a little closer, as you see here, this tank is nothing more than just two large containers right here and right here. And these are made of standard plexiglass. Each particular container here is 1 liter that can be filled. And as you see here, there's also a little knob here that allows you to control the flow of fluid from one container to the other. So right now, the position that the tank is in is, since the knob is horizontal, you are allowing fluid to flow in between both containers. And when you rotate this to the right, you will be closing the actual top portion here. And when you rotate this to the right at the bottom, you'll be turning off the circulation at the bottom. Now, in terms of setting up this experiment, the other items that you would need is first to have some food coloring. And this can be any one that you would get generically. This is picked up at a grocery store. I would recommend getting food coloring that is going to be red and blue so that you can have a clear distinction between the colors that will occur as the actual model is going forth. The next you would need would be your salt container, because you're going to be adding salt to one side of the system and seeing how the salt difference between the system is going to drive a circulation pattern. And then third, you're going to need some type of stirring rod. Now I'm choosing something very simple just to show that anything will work. So I'm just choosing a long ruler. And the basic idea is that the rod has to be long enough so that you reach the bottom, because you will be stirring the contents in both containers. And then lastly, you need to have some sort of water source. So I have some water here, and I have some spare water right behind it right here. Now, to set up this particular experiment, what we're going to do here is that we're going to look at, for the first experiment, only changes that occur when you have differences in salt content, which is called salinity differences between one side of the tank and the other. So the first step here is if you want to only measure the salt content differences, you need to make sure that the water temperature between both of your items are the same. So that means the easiest way to do that is to obtain a large vessel of water that has a uniform temperature, and you can verify that yourself by having a thermometer present, and then you're just going to pour water into the tank. Now, since both of these are open, that means when you pour water in here, you should notice that both tanks should be filling up. And after you fill this up, what you want to check is to see that both sides of your tank has approximately 1 liter. So in terms of this particular tank, just look at the corresponding levels and they are about the same right here. And both of these have the same temperature at this moment. You've now filled both of them up. So now what we're going to do is that we're going to now close the actual valves so that we can now separate the content on both sides. There. Now, what we're going to do is that we're going to add salt to one side and keep the other side fresh water. So going back to the standard salt that you get at the grocery store, you can just pick whatever chamber you want. I'm going to pick the one that is to my left. And you want to add a generous amount of salt to this. Now, what you should see is that a lot of the salt will have accumulated towards the bottom of the tank. So from this point, take your stirring rod and you're going to be stirring so that the salt itself begins to distribute itself evenly and begins to dissolve within the water. And this will probably take somewhere between 20 to 30 seconds to do. And one of the signs that you have stirred this appropriately and that you have a clear salt content difference is that you should see that the actual color of the water is going to be slightly different from fresh to salt water. Given there. So now the chamber here has salt that has been dissolved and evenly distributed throughout. The chamber over here is fresh water. So now the idea is that we want to figure out what should happen when we open up the chambers. So the way that we're going to do this properly is that we're going to apply food coloring to both sides. Now, my recommendation is to choose blue dye and to choose red dye. And the idea here is what I would suggest is to choose blue dye for the actual side of the tank that you think would have the largest density, whereas you would choose red for the part that you would think would have the smaller density. Now let's recall what density is in a nutshell. Density is a way that we describe how much stuff, how much mass, how much weight is packed into a particular object or into a small volume. So the more stuff you pack into an object, the higher its density will be. So that means if you were to guess at this initially, I added salt to the left chamber and I didn't add anything to the right chamber. So my expectation is that based upon that definition of density, I expect that the left chamber is probably going to have the larger density. Now, if that's my hypothesis, that means I'm going to mark that with blue, and I'm going to drop about 10 to 12 blue food dye drops in here. And if the left side is going to be blue, that means the right side will be red. And drop about 10 drops within there. And now you begin to see that the dye is going to try to distribute itself throughout. At this point, what you should do is that you can either wait for this to become evenly distributed, or you can use your stirring rod once again to mix the properties of both. So if I mix this around, you get a nice, well-established blue color. And make sure that you stir all the way to the bottom so that the color remains uniform all the way through. Now, if you stirred the bottom side with your blue, that means you need to wipe off your particular stirring rod so that you don't mix the food dye and so that you don't right now mix the salt content. So if I wipe that off and then use the opposite side of your stirring rod to stir the red side, and as you see, the red is more or less already well put together. So now you have your both sides well put together and well crafted. And now what we're going to do is that we're going to watch the process of having different salt contents generate a density circulation. So what I'm going to do here is that I'm going to bring this a little bit closer to the camera so that you can see what happens when we begin to stir this, when we begin to see this become well distributed. Now, right now, what we're going to do is just open up each individual chamber. So that means I'm going to start off with opening the top and then opening the bottom. So rotate this over and rotate this over. And if you look very closely at the top, you will begin to see that there is a flow of red coming over here. And if you look at the bottom, there's a flow of blue coming over there. Now, the idea is to watch what happens over time as the actual fluid begins to mix and begin to move. What you should begin seeing is that you had a flow of red going to my left, and you had a flow of blue going to the right. So that means if you were to piece that together in your mind, you must have had a circulation of fluid going left. And if you look closely at this, you're pushing this fluid down. So you have a flow of fluid going this way, flow of fluid going down, and then you have a return flow going this way. And we can wait a little bit longer to see the actual consequence of the whole process happening. So now notice, after some time, you see that you have a very well-established circulation that must have happened to cause the fluid to go from one chamber to another. But there's also something else very important to notice about what you are now seeing. So remember that both sides started with approximately 1 liter of water initially on both sides. And notice that approximately you have half red over here, half blue, and half blue below. Also notice that if you look at your actual density circulation tank, note that the blue is situated on the bottom of both chambers. And notice that the red is situated on top of both chambers. Now, you've probably seen something like this happen before when you look at the fluids that have different densities. So, for example, you probably have already seen what happens when you take water and oil and you put them in the same container. You notice that the water and oil separate such that you have oil sitting on top of the water. That tells you that there's a difference between the density of oil and the density of water. But the same thing is occurring right now. Remember that we said and that we mixed the actual blue dye in the portion of the tank that originally had the salt in it, and then the red was the original fresh water. So that means we have a less dense fluid, the red, sitting right on top of a more dense fluid, the blue, right here. And so this definitively tells you that salt content, when you add salt to it, the salt is going to increase the density of the actual water. But what you also saw was that in order for the fluid to basically circulate, you must have had the more dense fluid sinking down, and you must have had the less dense fluid pushing up. That was why you had red fluid going this way towards the top, and that's why you have blue fluid going down at the bottom. So this gives you a sense of why a circulation pattern would ever develop. And in terms of this particular experiment, what this is meant to teach you here is the fact that density differences not only cause a separation of the actual fluids, in this case, salty water to fresh water, but it also produces a circulation pattern that can be discerned and examined. Now, the last part of this video is important because it actually corresponds to things we actually see in the ocean. What I want you to notice is that when the actual mixing process goes, notice that the water in both tanks are not perfectly mixed. In other words, what you see here is that it is a very clear separation that happens between the fresh water and the salty water down here. Now, what that means is that none of this fresh water reached the bottom of this tank over here, and none of the salty water ever got back to the top over here. So that means if I was to actually look at the salt content going from the top here to the bottom, what you would notice is that the salt content is changing in a very specific and special way. Notice, for example, that the fresh water has a uniform color near the very top of this particular container. And notice that the salty water has a uniform color at the bottom. That's meant to tell you that the salt content is more or less even down here, and the fresh water content is more or less even here. But then notice that you have a transition zone right around here, where the red and the blue, they're not quite mixing to give you violet, but you have a strong change between the red and the blue. That means there's a sharp contrast between the fresh water boundary and the salt water boundary. The same thing happens in the ocean. In the ocean, we do not see that the density of the ocean is uniform going from the top of the ocean to the very bottom. Instead, what we see and what we observe in terms of everything that we know about ocean observations is that we have what is called a stratified ocean. We have a mixed layer of fresh water, and then we have a sharp change in the actual content. Sharp change in the density and saltiness somewhere below the surface. And then below that, we have a very different amount of density that is present. So that's our first main experiment. And so now what we're going to do is that we're going to explain why it is this whole process happens and how this leads to ocean currents and ocean circulations. Now let's apply the concepts from the experiment to what we observe within the oceans, which leads to ocean currents and ocean circulations. First, the ocean has layers of water that differ in terms of temperature. Overall, there is a three-layered structure in most of the ocean. The top layer of water is called the mixed layer. And this is the portion of the ocean seen in this figure where the temperature is relatively constant. The sun-warmed surface mixes with cooler, deeper water because of the presence of wind, breaking waves, and other sorts of currents. Below that mixed layer, we have what is known as the thermocline. And the thermocline is the region in the ocean where the temperature changes rather dramatically. In this picture, the temperature goes from a warm to a cold within the actual thermocline itself. Now, this thermocline tends to extend about 1,000 meters below the surface. And as was just stated, the temperature in this layer changes rapidly with the depth of the ocean. The thermocline separates the warmer mixed layer up top from the cooler, deeper layer that extends to the ocean floor, going down as you see here. Now, in our experiment, we examined the salt content, or the salinity. Now, salt in the ocean makes the ocean water more dense than fresh water, and that's what we observed in our experiment. That means the salinity is generally going to increase as the water depth gets lower and lower. So just as in your experiment, we saw that the freshwater portion was near the top of the actual tank, whereas the saltier portion was at the bottom. The region in which the salt content changes dramatically is called the halocline. And notice that the salt content goes from a small value to a very large value. Now, based on what we just argued, the temperature of the water affects the density, and so does the actual salt content. So due to those two changes working together, that means the ocean's density, generally speaking, increases as you get deeper into the ocean. So the combination of temperature changes and salinity changes leads to a sharp change in density at a region called the pycnocline. The term pycno corresponds to density changes. So notice the pattern seen in these three figures. As you get deeper into the ocean, the water gets cooler, and cooler water tends to be more dense than warm water. As you get deeper into the ocean, the salt content tends to increase, and that's because saltier water is more dense than fresh water. And therefore, there is a sharp contrast between the water density near the top versus the water density within the deep ocean. Now, this is important when it comes to understanding how circulations work within the ocean. So we'll start here by examining all of the circulation patterns that we see across the globe. Colder water and saltier water, as you just saw, is heavier than warmer, fresher water. Water gets denser in the higher latitudes near the North and South Poles because of the cooling that occurs in the atmosphere, and also because salt levels increase when water freezes. Now, the regions near the poles have very dense, very cold, and very salty water. But also, evaporation can also increase the salt content, because as seawater evaporates, the salt is left behind, and that will increase the overall salt content of that particular region. That's actually what happens in the Dead Sea and in the Mediterranean Sea. Differences in water density generate slow-moving currents due to the sinking of the colder, saltier water into the deeper parts of the oceans and the pushing and displacement of the lighter, less salty water upwards. However, as you saw with the tank experiment and as you see in this animation, deep water currents move very, very slowly, about 1 meter per hour or about 3 feet per hour. That's compared to the speed at which wind-driven water currents move, which is about 1 kilometer or about 0.6 miles per hour. So dense water will sink until it reaches an area in which you have even denser water. The water will then spread out horizontally as more water sinks behind it. And thus, as the dense water moves north, it is warmed up by the surrounding water, and as it warms, it becomes less dense, and the water will rise towards the surface. And that gives you the circulation patterns that we tend to observe overall in the oceans. Now, here's an experiment that you can try at home based upon what was just discussed in this video. And this is a variation of what we just did. One thing that you can do is to produce what we call a temperature inversion. So if you put warm salt water in one tank or one reservoir and put cold fresh water in another reservoir, what you may see is that the cold fresh water may float on top of the warm salt water. That is what we call a temperature inversion, where the colder water is at the top and the warmer water is near the bottom. This is a phenomenon that is observed relatively often in estuaries, in which you have cold, fresh water that sometimes floats on top of warm salt water. This is an experiment that you can do yourself, and this will show you which variable matters more when it comes to the actual density of the water. Does the salt content play a bigger role, or does the temperature content or does the temperature change or the difference in the water play a bigger role? The idea here is if salt content plays a much bigger role, that means you only need to add a small amount of salt to one tank and you should see that temperature inversion happen. In contrast, if temperature plays a bigger role than salt content, that means you would need to add a substantial amount of salt to see the temperature inversion occur. I suggest you do this and walk through and see how much salt is needed to cause a temperature inversion between two bodies of water with different temperatures.